Okay, so this is like sideways, isn't it? Is it sideways? It is sideways.
Yeah.
Okay. Okay, so maybe it can be a little closer then. All right. There. Okay. I think maybe that's got it. Okay, so 2.5, it's saying number 54, I believe. Number 54. Suppose that if f of x is continuous, and this is the premise for many, many problems you will be seeing in calculus, right? In order to have a certain level of nicety, we want to establish that it's continuous, at least somewhere, right? And where does it say it's continuous? Continuous on 5, the interval from 1 to 5. The closed interval, so that means it's continuous from the left at 1, and it's continuous from the right at 5. Sorry, the other way. The continuous from the right at 1, so you can approach 1 from the right, and continuous from the left at 5. And the only solutions to f of x equals 6 are x equals 1 and x equals 4. If f of 2 equals 8, explain why f of 3 must be bigger than 6. Well, I think we need a picture, right, to see what's going on here. And so for that, I will draw something over here. So the action is between 1 and 5. So here are 1, 2, 3, 4, 5 perfectly evenly spaced hash marks. And then we've got, we want to go up to 8, like 1, 2, 3, 4, 5, 6, 7, 8 on the y-axis. All right. And we know that the only solutions to f of x equals 6 are 1 and 4. So I'm going to plot those 2 points, right? If f of 2 equals 8, right? Okay. Explain why f of 3 is greater than 6. So basically, we know that okay, so how about proof by contradiction, right? So I'm going to try this proof by contradiction. And do you know how that works? The idea is you assume the opposite and you show that that leads to a logical contradiction. And so your assumption must be wrong. And so what you want to be true is true. So assume that there is on the interval between 2 and 4 such that f of a is less than 6. Okay. And the intuitive idea here, right, is that, if we're continuous and we're going from, here this is 2 and 4, right? If we're going from this point to this point on an unbroken curve, then if we were to go below, right, so that there's some value A in here such that f of A is less than 6, right? So that's f of A here, right? So f of A here is less than 6, right? So this is the point A, f of A. Then we violated something. What's the argument here? Then there would be another solution, right? So we violated the assumption that there are only two solutions to f of x equals 6. Okay, so then by the intermediate value theorem, and that is a very common abbreviation, right? IVT. So you should know what is meant when you see the abbreviation IVT. There exists, and it is an existence theorem, right? It says that there exists some for all n between I want to say f of 2, which is 6, right? And oh, I'm sorry, this is 8, right? And f of A, there exists, and that's the abbreviation for there exists. Is it okay if I use that? Because I'm running short on space here, right? Oh, and this is for all. Yeah, I didn't really explain that either, right? But these are common logical symbols you should get familiar with, right? So for all n between f of 2 and f of A, there exists C in the interval between 2 and A. Can I say such that? That's another common symbol, okay? So for all, maybe I'll put these up here, okay? This means for all. This means there exists. And this means it's like a little backward epsilon, such that. The language of logic, folks. So for all n between f of 2 and f of A, there exists C between 2 and A such that f of C equals n. Well, I argue, if n equals 6, since 6 is between f of A and f of 2, right, which is 8, there exists C in the interval from 2 to A such that, and I'm just going to write out such that, sometimes people write ST, f of C equals 6, which is a contradiction. All right, so that's the universal symbol for contradiction. Therefore, our assumption that there is A in 2, 4 such that f of A is less than 6 was false. Okay, so that's my explanation and I'm sticking to it. Any questions about that? Okay, shall we try then? So you see this intermediate value theorem is very sort of, you know, proof and logic kind of stuff going on. It's not so much computation. You're getting a feeling for the continuum, what it means to be continuous and the implications thereof, right? So the idea is that, you know, you can't cross this line. And if you can't cross that line, then there is no value. There's no input that'll give you something less than 6 in between, because it's a continuous function. All right, let's try another one. I'm looking at the exercises, which shall I? It's kind of curious. I can't. Okay, so there's maybe I need to have a separate window over here for that. I need to arrange my windows here. Okay, so this is the problems in this section. How about 55 through 58? Use the intermediate value theorem to show that there is a solution of the given equation on the specified interval. Oh, okay. Shall we try 55? Just to get a feeling for this. Okay. 55 then. And I'm going to look at that. Okay. So this is 2.5, number 55. And use the intermediate value theorem to show there is a solution to the specified equation on the given interval. Okay, so in this one we've got negative x cubed, oh no, it's a cubic, plus 4x plus 1. Omar Khayyam had some things to say about the cubic. And this is on the interval from negative. So this is the open interval. But we notice that, so first of all, you have to establish the premise of the intermediate value theorem, which is f is continuous on some closed interval, right? Well, here f is a polynomial. So shall we call this f? So since f is continuous everywhere, and I'm going to say on the set of real numbers, that's the symbol for the set of real numbers. Since f is continuous on the set of real numbers, and so we need to find a value where the output is negative on this interval and a value where the output is positive. So I noticed that it's positive at 0. How's it doing at -1? It's negative. Okay, great. So that's easy. F of -1 equals, I think it's -2 is less than 0 is less than f of 0, which is 1, by the intermediate value theorem. Since 0 is between, well, I mean, I've already sort of established that 0 is between f of -1 and f of 0. So I don't really have to say since. I've already, there exists, right? C on the interval from -1 to 0, such that, how about that abbreviation? F of C equals 0, and that establishes what we want, right? So that seems pretty easy, but you do have to go through the process of establishing that the premise, and it's a two-part premise, right? What are the two parts? One is the function is continuous on the closed interval, and this is continuous everywhere, so that was easy. The other is that you have a value n between f of -1 and f of 0 here, right? So 0 is between -1, f of -1 and f of 0. And so both premises of the, both parts of the premise to the theorem are met, and so the conclusion follows. How about another one of these? About number 58? I imagine some of these are going to be a little bit trickier maybe. So here we have f of x equals, oh, okay, so they don't actually say what f of x is. And so it's your job to choose f of x. And I'm going to choose it like so. So let's go back to the problem. Do you see? This is, I think, the problem we're looking at. Or can I click on it, make it bigger? Okay, I guess not. Some of these. Oh yeah. Huh. Remove highlight. Okay, there. Okay, so this is the equation they want us to solve. So we don't have a function where we could say the function is equal to some number, right? So if this equation is true, then the difference between the left side and the right side must be 0. So I'm going to look at that equation and say, because essentially here we have a function on the left and a function on the right, and which one do we deal with? So the trick here is to introduce a function which is true if and only if this equation is true. And the simplest way to do that is to say that the difference between the left side and the right side is 0, right? That's true if and only if this equation is true. So I'm going to then go in here and say that's my equation, right? And what's the interval? I don't know, it's obscured. Okay, on 1, 2. Okay. And so I don't know, what's f of 1? What's f of 2? Or do you want to pick out, sometimes there's some more convenient values, like pi over 2 is between those, right? Would it be easier to value? Well, again, I think let's just, shall we make a table of values? So here's x, here's f of x, and here's 1. So what's f of 1? Well, sine of 1. 1 is pretty close to pi over 3, right? Pi is pretty close to 3, 3.14. So sine of pi over 3 is pretty close to sine of 1. And sine of pi over 3 on a Wednesday is about square root of 3 over 2. Well, it's exactly square root of 3 over 2, which is approximately 0.866. Is this going to be less than? It's actually going to be less than 0.866. So I'm going to say about 0.85, just a wild guess. And so then the 1 minus 1 is going to be 0. So I'm going to say this is approximately 0.85. Maybe I'm off a little, right? But the idea is it's positive. This is not a negative sign. This is an approximation. There, how about that? So that's approximately 0.85. How about at 2? Now, well, 2 is on the other, that's into the second quadrant on the unit circle, right? And that's then about 0.5 bigger than pi over 2. I don't know. I guess we could just use a calculator here, right? But we know that it's going to be negative. How do we know it's going to be negative? Well, this number is, let's say it's 0.8 or something like that. It's got to be less than 1, right? This number is 2, so this sum here is going to be less than 3. And we're subtracting 4, right? So I'm just going to say it's negative, right? I don't even have to compute it, right? I've justified that it's negative and this is positive, right? And that's it then, right? So 0 is, since we have to establish the premise, right? F of x is continuous on the set of real numbers, right? Because why? Well, it's a sum or difference of continuous functions, right? A polynomial and the sine function is continuous everywhere. So a sum of continuous functions is continuous. Since f of x is continuous on the set of real numbers, in particular, then it's continuous on the interval from 1 to 2, and 0 is between f of 2 and f of 1. Therefore, by the intermediate value theorem, there exists, I suppose I could use my fancies there exists symbol C on the interval from 1 to 2 such that f of C equals 0 and the equation is true. All right, so that wasn't that bad. I don't know. So in 59 through 60, let me bring that up here. 59 through 60, they say, prove the equation has at least one solution. Use a calculator to find an interval. So here they don't give you the interval, right? Use a calculator to find an interval of length 0.01 that contains a solution. Okay. So I'm going to use the same sheet of paper. I think I can get by with that. Where am I over here? Oh, my mouse is over here. Okay. So this is number 60. And so prove that, and it's cosine x equals x cubed has a solution, at least one, they say. One solution. They say a real solution, but that's the only kind our mama lets us chew. And use a calculator to find an interval of length 1/100th that contains a solution. And okay, I'm going to just go to I'm now going to unveil my GeoGebra window. Yeah, how about that? And I think, so this one, the input is down here. This is a little different version of GeoGebra than you'd find online. There's been a lot of versions of GeoGebra. And why is my name down here? I don't know. That's, does it have to be there? It's kind of in the way, isn't it? I suppose I could move this up a notch there. Okay, so what's our function? Well, again, the difference between the left side and the right side, which I'm going to write here, x cubed minus cosine of x. And does that pass through 0? I bet it does. Yeah, right there, right? And so we'd like to know, where does that happen? Well, how do you find a solution to an equation like this? That is x cubed minus cosine x equals 0, right? How do we find that x-intercept? How do we solve that equation to find that x-intercept? Well, I mean, not to be cheesy or anything, but we could just say, here, I got my point tool, and I'm going to find that point this way. It takes a little while to figure it out, doesn't it? Yeah, it says, oh, you want that point? I got to do some calculations. And now notice I have a different sort of menu option. So I'm going to have to figure out, what do I do to get more decimals, right? Preferences. Yeah. I don't see it there. Input bar. How about we show it at the top? It would be a little bit easier for it at the top, wouldn't it? Okay. How about over here? Yeah, that's the problem with GeoGebra. There's so many different versions of it, and each one has its own quirky way of setting the decimal digits. Those are the axes. This is where you see things. This is line segment. Blah, 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 blah. I don't see anything here. Algebra, maybe? Cartesian coordinates? No. And this is just that. Degree radians. I don't blurt out if you see what I'm missing here, which is, oh, use localized digits. Yeah, that's all right. That's not going to help. All right, I'll close that window and say options. Oh, rounding. Okay, there it is. Options. Okay, so now we see we've got it accurate to 0.86547. Okay. I guess I'll just go over to my sheet and finish the problem then, because we now have the information we need, right? Which is that the equation has a solution in the interval from, and I just have to get my GeoGebra window visible here. So within 1/100th, huh? So I can say 0.086, 0.087, right? There. So that's an interval that contains the solution, which is going to be some irrational number, actually, right? So we can't write the solution exactly, as far as I know. Okay, so more good problems. I suppose we could move on. The good problems tend to be at the, oh yeah, so notice these monsters here, right? For what values of x is x continuous in number 71 there? And it's a piecewise defined function, which, you know, you separate out the output based on whether the input is rational or irrational. And for this, you kind of have to know the weirdness of the continuum, right? This sort of brings out the weirdness of the continuum. So let me ask you a question. Are there more irrational numbers or rational numbers? You might say it's a trick question. Maybe, do I need to look at the chat? The chat keeps disappearing on me. There it is. Nobody's. Maybe I should try making a poll. Oh, what happened? I completely lost my window. Okay. Have we tried polls? Add a question. Okay, I'm terrible at the few times I've tried to do a poll, I've really screwed it up. Oh, so then it wants me to sign in to something here? You can't see that either, can you? Yeah, over here. Yeah, all right, so I'm not going to do a poll then. It wants me to sign in. No. Let's see. Yeah, it's just the same thing again. I don't know why I did that. So what happened to get rid of the poll? I don't know. So the question is are there more rational or irrational numbers? And I guess it's a trick question, all right? Because there's an infinite number of both. But in fact, there are vastly more. I know they're both infinite, right? So it's kind of like, what? But there are vastly many, the irrationals are much more dense, let's put it that way. So if you were to throw a dart at the number line and it were to hit one point, the probability of it hitting a rational number is basically zero. It's just not going to happen. It's like almost all numbers are irrational. And if you think about, constructing a number as a sort of an infinite sequence of decimal values, like 0.1576809654431, etc. Like, to specify a number on the number line, you'd have to specify an infinite number of digits. And if that's a rational number, you would have to follow a pattern in those digits, like 0.1111111 repeating, right? That's a rational number. Or 0.123123123, that's a rational number. But if you pick a number at random, the probability of it like showing a pattern like that is essentially zero. So, however, between any two irrational numbers, two different irrational numbers, there are infinitely many rationals. And you can reverse that around, right? Between any two rationals, there are infinitely many irrationals. But the irrationals are much more dense. I'm just trying to give you a sense of the craziness of the continuum, right? And rationals and irrationals. So if you were to plot this function, you'd have to have, discrete points, right? Not on a continuum, right? Because if the input is rational, then you plot a point on the x-axis. And if the input is irrational, you plot a point on the line y = 1, right? And so, but none are, so there's also this problem of, is it possible for two different real numbers to be precisely next to one another? No, right? Because if they're different, then there's in fact infinitely many numbers in between, right? At least that's our conception of the real number line, the continuum. Okay, so for what value? So none, right? So this function is nowhere continuous. How about this function? This function is continuous at 0, right? Because I can always pick, because the limit as x goes to 0 of 0 is 0, and the limit of 0 as x goes to 0 is 0. And so the limit from the left, or the limit along this line would agree with the limit along that line. And so it's, but only at 0, right? So this function is continuous only at a single point. All right. I don't want to belabor that too much longer since it's now 8:50. We need to get on to 2.6 today, right? So if a and b are positive numbers, prove that this equation has at least one solution in the interval. I can't resist. Let's try to get to 74, okay? So I need to bring up my thing there, and okay, so this is number 74, huh? .5, number 74. Problem is to given A and B in the set of positive reals. Okay, so that little plus sign means positive. Okay, these are the set of all positive real numbers. Prove that A over x cubed plus 2x squared minus 1 plus b over x cubed plus x minus 2 equals 0 has at least one solution. So no matter what positive numbers you choose for A and B, this is going to have at least one solution in the interval from -1 to 1. Oh, yeah? Huh. All right, so I suppose we could just say this is our function, right? Is that a continuous function? Well, do we have vertical asymptotes anywhere? And in order to determine that, Well, I don't know. Should we try to combine these as a single rational number instead of a sum of two rational functions? So there's a bunch of things we got to think about, right? Are there problems in the domain, right? So we want it to be continuous on some interval. So I think we have to look at both denominators, right? So x cubed plus 2x squared minus 1 equals 0. Does that have a solution? If so, then we have a vertical asymptote. And if that asymptote is between -1 and 1, then we're going to be in trouble applying the intermediate value theorem here, right? So I don't know what's f of negative. What's sorry, not f, but what is this? This is a continuous function, right? It's a polynomial. So what is its value at -1? It's going to be 0. Oh, so it's got a vertical asymptote, right? Yeah. So in fact, since it's got a 0 at -1, that means x plus 1 is a factor, right? So I can factor out x plus 1. What's the other factor? Well, it's got to be an x squared. Then you got another x here, I think, and a -1. How are we doing? How about that quadratic then? That should also have zeros. Are they real zeros? Well, what's the discriminant? B squared is 1 minus 4ac is going to be 5 altogether, right? This discriminant is +5. That means that it probably has a couple of irrational solutions. Should we find them? Yeah, because they might be, between -1 and 1, right? So let's complete the square there, right? So we're going to have x plus 1 times the square of x plus a half. And then we need to add subtract 5/4. Yeah, because you'd have a quarter, you need to subtract 5/4 to get -1, right? So the other solutions are x equals -1/2 plus or minus the square root of 5/2, right? And are those between -1 and 1? Well, this is approximately -1/2. Who knows the square root of 5 offhand? 2.45, I think, something like that. 2.45. I should have a handheld calculator here. So if we were to, so x is approximately, there are two values, right? And if we were to add, we'd have half of 1.45, which is 0.725. And that's between -1 and 1. So we got a problem there, Houston. And then if we were to subtract, we'd have -3. Half of that is going to be -1.72, I think. Yeah, something like that. But that's not a worry. But this is a worry, right? That's between -1 and 1. So it's got another vertical asymptote there. Okay, so we'd have to restrict our interval to something less than -1 to 1, right? In fact, we might want to pick like -0.9. So it's got a vertical asymptote. So -1 is a problem and +0.725. What about that other one? We got another cubic here, right? So this is x cubed plus x minus 2 equals 0. Does that have an obvious? Yeah, that has an obvious 0 at 1, right? So x minus 1 is a factor. And what's the other factor? Well, x squared. I want to say plus the minus x. Yeah. And then plus 2. Yeah, just factored the cubic as a product. So I knew that +1 was a 0, So x minus 1 had to be a factor. And then I just used the sort of guess and check method for factoring. When you multiply this out, do you get that? Yeah, x cubed, then minus x. Oh, this should be a plus. Oh, there is no x squared. Okay, so I did that wrong, didn't I? So, yeah. So x cubed minus x squared minus x. So this has got to be a plus, right? Does that then work out? No, we get a. Oh yeah, it does, right? We get a negative x and a positive 2x. Those add up to x, and yeah, so it works out. Okay, but I did have it wrong at first, right? Okay, so what about the zeros of this guy? Well, let's complete the square there, shall we? So that's going to be x plus a half again, squared. And now the square of a half is a quarter, and I want 2, so I'm going to add 7 quarters. Oh, what's the discriminant here? B squared minus 4ac is going to be negative, right? So I didn't really have to do this because it doesn't have any real zeros, so nothing to worry about there, right? So since here we have a plus sign, so a square is positive. You add something to that, you can't get 0, right? So over here we had a problem, right? Because we're subtracting, and so we do get a real 0 at this trouble point. Well, there's 2 real zeros here for the quadratic. Here, there's no worries, right? But we have, so we have 3 vertical asymptotes to worry about here, right? Are we worried about the one at 1? Not so much, because we kind of ruled that out, unless that's, oh, well, maybe a little GeoGebra action here, folks. So I'm going to bring that up, and then we need to get on to 2.6. And where's my case? So can I just delete that? How do you delete a function here? Oh, that's the picture of the function. I get confused. Okay, so here. I just want to delete that. I can erase it. I can collapse it. Delete. Okay, so I right-clicked on it and deleted it that way. Okay, so now I'm going to enter a different function. Let's a couple of sliders. Here's a slider for A. Sure. And here's a slider for B. Okay, we can edit those later if we need to, right? So can I move them? Whoop, not that, but this. Oh, I want to move the whole slider. No, it won't let me. It'll only let me slide. Can I? Nope. Move the slider. No, this is, won't let me do it. Okay, that's fine. I guess it doesn't matter where it is. I'm sure there's some way of moving it, but never mind for now. So I've got my function, which is now going to be a divided by x cubed, get out of the exponent, plus 2x squared and minus 1, right? Okay, that's the first term. And it doesn't, it's made that red, right? For some reason I have, oh, cubed. Okay, so now you can kind of see that asymptote at 0.7, right? Or near 0.7. And we're going to add to that, or maybe we should make that one function and then have a different function here, b divided by x cubed plus x. Oh, that's weird. Okay, plus x minus 2. Okay, now I'm going to sort of hide both of those, right? And make another function, which is f of x plus g of x. So that's then the combination of those, right? Oh, enter. And that's this orange function. Okay, it's orange. What are you going to do? And you see, okay, so what prove that has at least one solution in the interval. Okay, wait. So we're not